Hello everyone. In this problem, we are given a string S and a list of words. Our goal is to find how many words are a subsequence of the string S. So in this example, we would return 3 because ABD, BCG, and BDFG are all subsequences of S. Some constraints of this problem are that the characters in S and words will only consist of lowercase English characters, and each word in the words list will consist of only 50 characters. Now that you understand the problem, let's try and come up with a solution. For our first solution, let's start with a single word and see how we can check if it is a subsequence of S. We can take a greedy approach with 2 pointers, I for S and J for the word. Our conditions for moving the pointers are, if the letters match, we increment both pointers, but if they don't match, then we move only the I pointer so that we can try for the next letter in S. If the J pointer is able to make it to the end of the word, we can say this word is a subsequence of S because it means it was able to find a matching letter in S for every one of the letters in the correct order. Let's go through this example. To start off, A does match, so we enter the if case and increment both pointers. Next, B matches, so we increment both pointers again. Now C does not match D, so we increment only the I pointer. Next, D matches D, so we increment both pointers. And at this point, we have reached the end of the word, so this means ABD is a subsequence, and we would increment some total counter. Now that we understand that this is the strategy for one word, there's no reason we can't do this processing for all words in parallel. So if there are 4 words here, we would try and match the pointers for all of them simultaneously. Here only word 1 matches the A, so we move the J pointer in addition to the I pointer for S. For this next iteration, we see that word 1, 3, and 4 have a matching B to S. So we increment those, and so on and so forth. Hopefully you get the idea. So let's look at the code. First, we have this list called match index, which is going to hold the index value of the letter for each of the word in words we are trying to match. From earlier, it was these JKLM indices. We also have the matching variable, which is the amount of matching subsequences. This is what we return as our final answer. For each character in S, we iterate through the index for each word and try to match the characters. If there is a match, then we increment the index for that word. If the index has made it to the end of that word, we increment the matching count by 1, and we also have a check at the beginning of the for loop. If the index has already reached the end, then there's nothing to check, so we continue to the next iteration of the for loop. For the time and space complexity of the solution, let's have n be the length of S, and m be the amount of words in words. Our time complexity is n by m. N is for the outer for loop, iterating through S. M is for the inner for loop, which iterates through each word in words. For space, we have O of m for the extra space used by the match index. And that's really it for the initial solution. Let's try and improve it further. There's actually no way to improve the asymptotic time complexity of the solution, but there is a way to improve the more practical time complexity. To do that, let's look at what is costing us time in the previous solution. The costly steps are the n iteration for S and the m iteration through the letters. Let's focus on the inner m for loop. The goal of the inner for loop is to identify the words that have a matching letter to the current character from S we are iterating on. Currently, this inner for loop is guaranteed to iterate m times for every iteration of n. We can reduce how many times the inner for loop runs in practice by using a dictionary where the key is a letter and the value is a list of words indexed under the key of the letter we are trying to match with S. So from earlier, rather than keeping track of these JKLM indices, we would have this dictionary indexing by the character that each word is trying to match. So to start off, it is the first letter for each word, so ABD goes under A, BCG and BDFG go under B, and CAF goes under C. On the first iteration, we are letter A for the S string, so we take the words indexed under A and move them to the next letter they are looking for. So in the case of ABD, the next letter is B, so it goes under the B. We also splice off the letter we just matched, which is the A. On the next iteration, the letter in S is B, so we take each word in the B list and move it to the next letter, and we repeat this process for every letter in S. If we encounter a match and that was the last letter, then we know we have found a subsequence and can add 1 to our counter. Here's what the code looks like. We have our dictionary, which I've called buckets. We initialize the starting value of this dictionary by just appending all the words to the bucket of their first character. Next, we get into the main part I was demonstrating earlier, where each character in the string, we save the list of words indexed under C, and then we reset the list. For every word in the bucket, if the matching word is just one letter long, it means we have matched that last character, and we increment the counter and forget about that word. Else there's another letter we have to match, and we append it to the list keyed under the second letter of the word, which is the word index of 1, and we append the word with the first character spliced off. And obviously at the end of the algorithm, we return the matching count. For the time and space, like I said earlier, the worst case time complexity stays the same at n by m. This happens when all the words keep matching and all of them have been moved every time. But this is a rare case, and in all other cases, the practical time complexity is better, because in most cases, for each letter in S, we only have to iterate through the subset of words which happen to be matching that letter in S. For space, it remains the same. The dictionary can grow to O of m, one value per word, and there is a max of 26 keys because all the words in words have to consist of lowercase English characters. Okay, that is it for the solution. Hope this video helps. Thank you for watching, and good luck on all your interviews.